other interesting examples of parametrizations. So this one, find the parametric equations for the cycloid generated by a point P on the unit circle. Well, what is a cycloid? It's a curve traced by a point on the circumference of a rolling circle. So let's say that we have, a circle here, and we're going to look at this point. As this circle rolls along, this point is going to move along this path. So like, maybe, when right here, it will end up over here let me draw this point right here. It will be down here and stuff like that. So as the circle rolls, imagine taking like a penny or something like that, marking a little dot on it and letting it roll along the ground. That dot will go up and then it will come back down. So our job is to figure out a parametric equation that will trace this out. We're assuming unit circle, so we're assuming that the radius of our circle is 1. Okay, so how do we do that? At time t is equal to 0, we're assuming that P is at the origin 0, 0. T, our parameter, is going to represent the angle our circle has rolled. So when it rolls 2 pi radians, we'll have made one complete loop around the circle. The point will be back at the bottom. That all kind of checks out with our picture here. So the thing to observe is that at time t, the circle at time t, circle has rolled t units along the x-axis. Okay, let me draw a picture here to better illustrate what's going on. So right here is our circle of radius 1. And so what we are assuming here is that we are forming an angle here, t. So right now, our circle is rolled t radians. At the beginning, this pointing straight down, it's rolled 0 radians. Now it's rolled some number of radians, t radians. In this picture, it's clear t is somewhere between 0 and pi over 2. It looks close to pi over 2 here. What are the coordinates of this point right now? Well, right now, this is t down here. And if we just kind of pop out a little triangle here, so that's t right there. Our circle has radius 1, so we have t and 1. And so these two sides are going to be sine of t and cosine t respectively. And that's just basically from definition. Sine of t is, sine of here is this length divided by this length. So almost by definition, we have sine of t and cosine t right there. Okay, so take a look at what's going on in the picture. What's our x value? If this whole thing is t, and this distance is sine of t, that indicates x is t minus sine of t. And what's our y value? Well, this is 1, and this is right in there. That's cosine of t. So y is going to be 1 minus cosine t. So putting all of this together, our parametrization is going to be c of t is t minus sine t and 1 minus cosine t. So let me point out sine of t and cosine t can be both Sometimes they're positive, sometimes they're negative. So when cosine t, so when t is pi, cosine t is -1. So the y value is actually 2. That's the maximum right here. That all checks out. Sometimes our point is behind the center. Sometimes our point is ahead of the center. That's all fine and well. Sometimes sine of t is positive. Sometimes sine of t is negative. So that's a kind of fun and historically important example, the cycloid. One last example, interesting example here in this video, predator-prey models. This is something that comes up a lot in differential equations, but we can just kind of imagine, drawing this kind of curve here. So suppose that we have some predator and some prey, and x of t is the population of the predator at time t. Y of t is the population of the prey at time t. So, for example, x of t might be how many wolves you have, and y of t might be how many rabbits you have. I'm assuming that wolves eat rabbits here. And so let's kind of think about what's going on here. As, up here, at this point here, we have lots of both predator and prey. And so what's going to happen is that because there's so many predators, they're going to eat the prey. And so maybe a better point to start off is down here. This is where we have, let's see, do I have the arrows going on here correctly? I do have the arrows going on here correctly. So let me back up, regroup my thoughts, and just kind of put it in this way. You might say, it's like, okay, we have not too many prey at some point, and not too many predators. But if there's not too many predators, the prey could increase in population until we have lots and lots of prey. And then at that point, because we have more and more prey, there's more food for the predators to eat. And so the predator is going to eat the prey. And then the number of prey is going to start going down. But because you have fewer prey, there's not enough food to support the predators. So the number of predators is just going to go back down. So you end up with a kind of loop like this. Again, this comes up a lot in differential equations.